Welcome to this rigorous scientific lecture on one of the most important experiments in physics history, how Ernest Rutherford discovered the atomic nucleus through careful analysis of rare, large-angle scattering events. Today we're going to walk through Rutherford's discovery as a step-by-step student workflow. This will teach you not just what he found, but how he approached the problem scientifically. Step 1 in any scientific investigation is to define your null model. What do we expect to see if our current theory is correct? In 1908, the accepted model of the atom was J.J. Thomson's plum pudding model. Positive charge was thought to be spread uniformly throughout the atom, with electrons embedded like plums in a pudding. Here's the plum pudding model. The positive charge fills the entire volume of the atom uniformly. Electrons are scattered throughout like plums in pudding. Under this model, when you fire alpha particles at atoms, you should only see small deflections. Why? Because the positive charge is spread out, so the electric field at any point is weak. The null model predicts deflection angles theta less than 1 degree. Any alpha particle passing through should experience only gentle nudges from the diffuse positive charge. Let me pose a question. Why exactly would deflections be small in the plum pudding model? The answer lies in charge density. If positive charge is spread over a large volume, the charge density is low. Electric force is proportional to the amount of charge in a small region. Coulomb's law tells us force equals K times Q1 Q2 divided by R squared. If Q2, the positive charge nearby, is small because it's distributed, then the force is small. Think of this analogy, walking through fog versus hitting a wall. In the plum pudding model, an alpha particle walks through fog. There's resistance, but no sudden impact. You'd expect gradual, small deflections. Step 2. Collect a large dataset. Rutherford, working with Hans Geiger and Ernest Marsden in 1909, began firing alpha particles at thin gold foil. Here's the experimental setup. Alpha particles from a radioactive source are fired at a thin gold foil. A zinc sulfide screen detects where particles land after scattering. Why gold? Gold has a high atomic number, meaning each atom has many protons, which should produce stronger scattering effects. Gold is also extremely malleable, so you can make foils only a few hundred atoms thick. The gold foil was approximately 400 nanometers thick. That's about 1,000 atoms thick. Thin enough that most particles pass through, but thick enough to interact with many atoms. Over weeks and months, they collected thousands of scattering events. Each time an alpha particle hit the screen, it produced a tiny flash of light. Geiger and Marsden sat in the dark, counting these flashes by eye. Step 3. Check for instrument bias. Before drawing conclusions, you must verify that your measurements are not artifacts of your equipment. Control experiment number 1. Remove the gold foil entirely. Fire alpha particles with no target. Result? Particles travel in perfectly straight lines. No scattering without the foil. Control 2. Vary the foil's position and orientation. If scattering were due to air currents or detector irregularities, changing foil position wouldn't matter, but scattering patterns changed consistently with foil position. Control 3. Test with different materials. They used silver, aluminum, and copper foils. Results scaled with atomic number, suggesting the effect was real and material dependent. After these controls, they concluded the scattering was a real physical phenomenon, not an experimental artifact. Step 4. Isolate the tail of the distribution. Most alpha particles pass through with small deflections, exactly as predicted. But what about the rare events? Let me show you the distribution. Plot deflection angle on the x-axis and number of particles on the y-axis. Most particles cluster near 0 degrees, forming a huge peak. The vast majority, 99.99%, scattered at angles less than 3 degrees. This matched the plum pudding prediction perfectly. But then, in the tail of the distribution, something astonishing appeared. Roughly 1 in 8,000 particles scattered at angles greater than 90 degrees. Some even bounced straight back. Imagine an alpha particle traveling at high speed, hitting the foil, and bouncing straight back toward the source. This should be impossible under the plum pudding model. Rutherford later said, It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Step 5. Test whether rare events repeat. Rare events could be statistical flukes or experimental errors. You must verify they're reproducible. Geiger and Marsden repeated the experiment dozens of times over months. Each time, roughly 1 in 8,000 particles scattered beyond 90 degrees. The ratio was consistent. With thousands of trials, this was far beyond random chance. The probability of this pattern occurring by accident was essentially zero. The large angle scattering was real and reproducible. Now we ask the critical question, what could possibly cause such enormous deflections? What physical mechanism allows a tiny alpha particle to reverse direction? Step 6. Propose a new model. Rutherford reasoned that large deflections require large forces. Large forces require high charge density. Therefore, positive charge must be concentrated. Rutherford proposed a radical new model. All the positive charge and most of the mass are concentrated in a tiny nucleus at the center. Electrons orbit far outside. Here's the nuclear model. A tiny dense nucleus contains all positive charge. Electrons orbit at large distances. Most of the atom is empty space. To understand the scale, imagine the atom enlarged to the size of a football stadium. The nucleus would be smaller than a grain of rice at the center. The rest is empty space. Let's do a back-of-the-envelope calculation to estimate nuclear size. We know alpha particles approach closely before scattering. How close? At closest approach, kinetic energy converts to electrical potential energy. E kinetic equals E potential. 1/2 m versus squared equals K times Q alpha times Q nucleus divided by R, where R is the closest approach distance. For alpha particles with energy 5 megaelectron-volts, solving gives R approximately 10 to the negative 14 meters. That's about 100,000th the size of the atom. This incredibly small nucleus creates an intensely strong electric field very close to it. An alpha particle passing near this concentrated charge experiences enormous force, causing large deflections. Step 7. Simulate expected angles under the new model. Rutherford derived a mathematical formula predicting how many particles scatter at each angle. The Rutherford scattering formula, n of theta, is proportional to 1 over sine to the 4th of theta over 2. This predicts the number of particles scattered at angle theta. This formula has a remarkable feature. It predicts a power law decay. Small angle scattering dominates, but large angles are still probable, just much rarer. If we plot the Rutherford formula, we see exactly this behavior: a huge peak at small angles, then a long tail extending to large angles. This matches the experimental data perfectly. Let's calculate the predicted ratio. For 90-degree scattering, sine of 45 degrees is about 0.7. 1 over 0.7 to the 4th is about 4. Comparing 1 degree to 90 degrees, the ratio is approximately 10 to the 8th. So large angle scattering should be extremely rare but not impossible. This matches observation. Step 8. Validate the model by systematically changing experimental parameters. If the nuclear model is correct, predictions should hold under varied conditions. Prediction 1. If you double the foil thickness, you double the number of nuclei encountered, so scattering rate should double. This is a linear relationship. Experimental test. Marsden used gold foils of varying thickness from 200 to 1000 nanometers. He plotted scattering rate versus thickness and found a perfect linear relationship. The data points fell on a straight line. This confirmed that scattering was due to individual encounters with nuclei, not collective effects or multiple scattering. Step 9. Change particle energy. The nuclear model predicts that scattering angle depends on how closely particles approach the nucleus. Higher energy alpha particles penetrate closer to the nucleus before being deflected. This means they should experience stronger forces and scatter at larger angles. Minimum approach distance Rmn is inversely proportional to energy E. Double the energy, halve the approach distance. They use different radioactive sources producing alpha particles of different energies, ranging from 4 to 7 mega-electron-volts. Result: the scattering patterns changed exactly as predicted. Higher energy particles produce more frequent large angle scattering. The Rutherford formula predicted the energy dependence with stunning accuracy. Final validation. Test with different target nuclei. If nuclear charge varies with atomic number, scattering should scale accordingly. The Rutherford formula predicts scattering rate is proportional to z squared, where z is the atomic number, the number of protons in the nucleus. Test. Compare aluminum with Z equals 13 versus gold with Z equals 79. Gold should scatter approximately 36 times more frequently than aluminum for the same angle. Experimental result. The ratio was measured to be approximately 37, in excellent agreement with the z-squared prediction. This provided independent confirmation of the concentrated nuclear charge. Let me ask another question. Why did this discovery take so long? Scientists have been studying atoms for decades. Why didn't anyone discover the nucleus earlier? Answer. Rare events are psychologically easy to dismiss. When 99.99% of your data looks normal, you might ignore the 0.01% that looks strange. Rutherford's genius was recognizing that those rare events were not noise, but signal. By collecting massive datasets and carefully analyzing the tail of the distribution, he found the truth. Let me summarize the complete scientific workflow we've traced through Rutherford's discovery. Step 1. Define your null model. What does current theory predict? Step 2. Collect a large, high-quality dataset with sufficient statistics. Step 3. Systematically check for instrumental biases and artifacts. Step 4. Don't ignore outliers. Isolate the tail of your distribution and analyze it carefully. Step 5. Ensure rare events are reproducible, not statistical flukes. Step 6. When data contradicts theory, propose a new model that explains the anomaly. Step 7. Mathematically derive quantitative predictions from your new model. Step 8. Validate by systematically varying experimental parameters. Step 9. Demand quantitative agreement, not just qualitative trends. Rutherford's discovery of the nucleus in 1911 revolutionized physics. It showed that atoms are mostly empty space, with mass and charge concentrated in a tiny nucleus. This discovery led directly to the development of quantum mechanics. Niels Bohr used Rutherford's nuclear model as the foundation for his quantum theory of the atom in 1913. The nuclear model explained chemical periodicity, atomic spectra, and countless other phenomena that were mysterious under the plum pudding model. Most importantly, it opened the door to nuclear physics, leading to our understanding of radioactivity, nuclear fission and fusion, and the energy source of stars. What lessons can modern scientists learn from Rutherford's methodology? Lesson 1. Don't ignore anomalies. The most important discoveries often hide in the data points you're tempted to dismiss as outliers or errors. Lesson 2. If you want to study rare events, you need massive datasets. 1 in 8,000 events requires tens of thousands of measurements to characterize properly. Lesson 3. Always run systematic controls. Extraordinary claims require extraordinary evidence, and that evidence must rule out instrumental artifacts. Lesson 4. Derive quantitative predictions. Qualitative hand-waving is not enough. Your model must predict numbers that can be tested. Lesson 5. Systematically vary experimental parameters. A good model should make correct predictions under a wide range of conditions, not just one special case. Rutherford's discovery demonstrates the power of the scientific method when applied rigorously and thoughtfully. From careful observation of rare scattering events to a complete revolution in our understanding of matter, this is science at its finest. The crucial lesson is following your data wherever it leads, even when it contradicts established theory, even when it seems impossible. This workflow, this systematic approach to anomaly investigation, applies far beyond atomic physics. It's a template for how science progresses toward truth.